Okay, we're going to start doing our first example of a related rates problem. I'm going to read the problem first. It says a kite 100 feet above the ground moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string have been let out? Well, the very first thing I want to do is recognize that this is a related rates question. How can I recognize that? Well, if we read along, we see that it says at a speed of 8 feet per second. Well, that's a rate. That's great. Next, they say, at what rate is the angle between the string and the horizontal decreasing? So they gave us a rate, 8 feet per second. They asked for a rate. We'll figure out exactly which rate next. Meanwhile, we're absolutely in a related rates question. So let's go sit down and go through the process about doing it. Here we go. Now, the first thing I want to do after I recognize that it's related rates is I'd like to draw a picture if possible. This is a nice simple picture. What I'm going to do is draw the ground. Yay. Then I have a kite that's up here. So that's my idea of a kite. Then we have string being let out to the kite that goes like that. We know that the kite is always 100 feet above because it's moving horizontally. So I'm just going to put a little 100 in here. Now they want the angle between the string and the horizontal. So that's going to be this little angle right in here. So I think I've labeled a lot. I want to start looking at the stuff they gave us. They said the kite is moving at the rate of 8 feet per second horizontally. What I'd like to do is label enough so that I can look at my picture and say this is what's changing at 8 feet per second. And right now I don't have enough labeled because the kite isn't changing at 8 feet per second. The 100 isn't changing, the angle isn't changing at that rate. What is changing at exactly the rate they gave us is this distance right here. So what I'm going to do is call that x. And then I'm going to be able to say that the rate they gave us, dx dt, is equal to 8. I'll put the units in at the end. I'm going to be a little pushed for space here. Now the next thing they do is they ask for a rate. They want to know how fast theta is changing. Well, how fast theta is changing is a derivative. Very specifically, it's the rate d theta dt. I'm just going to put a little question mark because this is the rate they gave us. This is the rate they're asking for. Now the next thing I absolutely need is a relationship, not between the two derivatives, but just between the two variables. Now, if I want that, the Pythagorean theorem isn't going to be helpful, right? Because x squared plus 100 squared equals the hypotenuse squared doesn't involve theta. What I need is a trig function. In fact, the trig function I need has to involve the opposite and the adjacent. So we know that the trig function that involves the opposite and the adjacent is tangent. So I'm going to start writing tangent, like that, of the angle is equal to the opposite over the adjacent, like that. Now the next thing we want to be able to do is take the derivative of both sides with respect to x. So I'm going to take, and we should always basically say this, with respect to t. And we'll talk about that in just a second after I write down writing the words both sides. How do I know I'm supposed to take the derivative with respect to t? Because I have a t here and I have a t here. Taking the derivative with respect to x is not going to be helpful there. All right, so what I'm going to do is to give myself a little bit of room so I'm not quite so squished. And hopefully we can work our way through. So I'm going to go like this, I'm going to go like this, and I'm taking the derivative of both sides with respect to t. Now, theta is not t. In fact, it depends on t. It's a function of t. It is a blob. So when I take the derivative of the left-hand side, I'm going to take the derivative of tangent blob. The derivative of tangent blob is secant squared blob times the derivative of the blob. So I'm going to go like this. Remember, it's not theta prime. Now, t is the variable, and we have to be very explicit about that. It's very important in the client disciplines, so physics and chemistry and biology. That they see those variables. And now I need to take the derivative of the right-hand side. Well, that's 100 times x to the minus 1. We've done this a number of times, so I'm just going to start writing the derivative out here. I have 100 over blob. That's going to be minus 100 over blob squared times the derivative of the blob. Just like that. Now remember, what we're being asked for is d theta dt. So I want to get d theta dt on itself by one side and see what I can do with it. What am I going to do? I'm going to multiply both sides by cosine squared. Cosine squared times secant squared is 1, so that immediately gets rid of the secant squared. So I'm multiplying the left-hand side by cosine squared. I get d theta dt. On the right-hand side, I get, oh boy, cosine squared times minus 100 over x squared times dx dt. So we can see that in order to find d theta dt, I need to find cosine squared. I need to find minus 100 over x squared. I need to find dx dt. Now, here we go. I have no idea what x is. There's information in the problem that we haven't used yet. They didn't want to know what d theta dt was. They wanted to know d theta dt when 200 feet of string had been let out. Well, here's something I can't do. I can't label this 200. Because if I label that 200, x is changing, but the 200 is not, right? So that's a really, really bad thing. We know it's changing. In fact, the word variable comes from vary, which means change. So I'm going to call that something. I usually use x's for horizontals and y's for verticals, and what's next in the alphabet is z. So I'm going to call that a z for the moment. All right. Now, notice, by the way, we're not being asked what z is. They do tell us that at a moment in time, z is 200. And here's something I'm also not allowed to write out. Z equals 200. If I write down z equals 200, I'm saying z equals 200, and I have the same problem I did before. So this is a compromise in terms of notation. What we can do, let's just put a little parentheses around 200, which means to us, we're going to put 200 in for z eventually. But not right at the moment. All right, here we go. Going back here, I need cosine squared, I need minus 100 over x squared, I need dx dt. I need to know x. So let me just get rid of this for a moment. And we'll do just a little bit of arithmetic. What do we know here? I know x is going to be the square root of 200 squared minus 100 squared. And I believe that's the square root of 30,000. Which is pretty darn big. But knowing that allows me to actually fill in all the stuff at the bottom of the equation. So here we go. What is cosine? Cosine is going to be, fact is I'm not supposed to do that. I'm supposed to do this. There we go. Yes. At the moment we're interested in, right, cosine is the square root of 30,000 over 200. But it's being squared. So what I get here is 30,000 over 200 squared, which is, I think, 3/4, but we'll worry about that in a little bit, times minus 100. Now, in the course of doing this, we saw that x was the square root of 30,000, so this is just 30,000. I'll go like this, right? Times dx dt, which they told us was finally 8. So what am I going to get? How about if we put a conclusion up here? So we're going to do this. So d theta dt equals, well, the 30,000s cancel. Now one of the 100s cancels with one of the 200s. So what I'm going to get here actually, I believe, is 2 times 200. So what I'm going to get here is 8 over 400. Which is 1 over 50. And what are the units? Well, even though theta is an angle, it's not in degrees. The reason we know that is because if we try to take the derivative of sine or cosine in degrees, pi over 180 starts flying all over the place. This is one of the main reasons why in calculus you always do things in radians. So this is going to be in radians per second. Now, if you don't like that, what we can do is convert to degrees per second. Let's see here, what do? I know that a 2 pi has to go down here. I know a 360 has to go up here like this. That's going to be about, what, 300? Well, it's going to be 100 pi is going to be about 300. So it'll be 360 over 2 pi. That's about, I don't know, 1.5 degrees per second or something like that. That's not bad. So let me just put the 360 there on top. and the 100 pi on the bottom. That is degrees, that is per second, and we at least can have some idea of how fast the angle is changing. And that's that problem.